Engineering magazine. Thank you very much for joining us. Now, normally when I'm on a plane, I try to sleep, read, watch a movie, but not exactly that's what 17-year-old Raymond would do. When he's on a plane, he thinks about what happens when the person next to him sneeze or cough, specifically what happened to the particles inside the tight airline cabin. So I want to understand a little bit about Raymond. Let's meet this young man first. Raymond, could you say a few words about who you are and tell us what you do?
Sure, yeah. I am a 17-year-old student here in Vancouver, Canada, and I've been doing science and engineering work ever since grade 7. And most recently, I took a project to the International Science and Engineering Fair, also known as Intel ISEF. And
Mm.
basically, what I was able to do with this project was I conducted both physical and computational simulations with aircraft airflow inside your typical 737. So all those commercial airliners. And basically, I was able to not only understand the airflow inside the aircraft better, but also come up with a solution that actually, for for a very economical cost, can overnight, when installed in the cabin, improve airflow by essentially decreasing pathogen transmission by about 55 times and increasing pressure inhalation by up to 190%.
That is an incredible fix. We're going to hear a little more about that in great details. Now, people might get this wrong idea that when you're trying to do this exercise, you may be going around in different airplane corners and sneezing around and coughing to see how things travel through. That's not exactly what you did. You did some sort of software simulation, as you just explained it to us, and the software they use come from Ansys software, and Ansys software is represented by another guest who is on our Hangout session here, and this is Gilles. Gilles from Ansys, welcome, and would you mind saying a few words about what you do at Ansys, and maybe
Hey,
also something about what Ansys does?
yeah, no problem at all. Hi, Kenneth, and hi, Raymond. Really a pleasure to talking to you today. So I'm responsible for the Ansys academic program in the western part of North America. But let me come back a little bit and tell you about what Ansys does. What we see is a lot of companies are adopting virtual prototyping at a very fast pace and rely on Ansys to do so. What does that mean? That means that the so-called traditional design, build, and test development process is being replaced by simulation-driven product development, where engineers are using simulation to test design very early in the development process, exploring many design, optimizing them using simulation, using virtual prototyping. Really what Ansys does is Ansys simulation technology enables companies really to predict with high level of confidence that their product will thrive in the real world. And really at the end of the day, customer trust our software to help ensure the integrity of their product and really drive their business success through innovation. So seeing all this trend, it is very important that students are exposed to simulation tools very early on. We need to make sure students understand the value of simulation and are able to add that to their resume, really to create a great career boost for them. And that's really my role. My role is to make sure that each and every student has access to simulation, understand its value, can learn about it in class, also learn about it with all the free tools and resources we provide to them.
Okay, very good. Stick around. I'm gonna, for the time being, ignore you if you don't mind me, because I want to hear the story from Raymond first.
Not at
But
all.
I will have some questions. I will have some questions, and I'll need you to clarify for me. Back to you, Raymond. Let's start by talking about this science and engineering fair that you enter. You have a number of other options to explore and different things you can look at, but why this specific scenario in particular? What fascinates you about that?
Yeah, so basically, I've been doing science and engineering for many years. It started out in grade 7. I basically did this project that takes the energy of falling precipitation and it converts the impact energy into electricity to help power the home. And it's basically this roof tile you can use to replace traditional roof tiles on like your typical house. And so I did a couple of things with renewable energy. I then explored the fields of biomechanics. So I designed this dynamically supportive knee brace in grade 8. And just last year, I created essentially a self-cleaning outdoor garbage bin, coupling, interdisciplinary techniques such as, working with embedded systems and electrical engineering, and doing that sort of work. But this year, really, my project, I kind of took my project to a whole new level, and I decided to take a look at aircraft airflow. And the reason behind this is that, especially with the recent epidemics of SARS, influenza, it's and most recently Ebola. It's very what we find is that work done to the inside of an aircraft cabin is very limited. There's tons of money spent studying the outsides of aircraft and making sure the aerodynamics are right. You're getting your fuel efficiency. But really, there's another aspect of flying that matters to the passengers that hasn't really been looked at that much in the past. And so, moving into this, this sort of was what inspired me to pursue my project this year. And fortunately, I was able to take that to the Intel International Science and Engineering Fair. In the past, I've attended things like the Canada-wide Science Fair, Google Science Fair, and really it was awesome being at the International Science Fair because what we find at ISAF is over 1,700 people selected nationally from over 75 different nations. And it's amazing to meet so many people, and it was such an honor to actually come first out of all those projects with this research that I've been doing with aircraft.
Raymond, in some of your projects, I'm sure you have the option to run physical tests. For instance, the roof, things like that. You might be able to build a scale model and test out your theories and things like that. In this case, I get the feeling that your access to an airline cabin, empty cabin that you can experiment with to test out your theory is somewhat limited. So tell us how you managed to figure out what you cannot do in physical thing you can probably do digitally.
Yes, so absolutely. So when you start looking at existing research that's been going on with aircraft cabin airflow, what we find is that CFD is actually the preferred method of studying these sorts of scenarios. This is because the issue with things like studying like a one-to-one physical aircraft model is that you actually get very limited resolution with techniques like particle velocimetry, and really you're not getting a full understanding of what goes on inside the aircraft cabin. And this is why people have been trying to tackle this issue through CFD, but what we've seen in the past is a number of issues that have limited the accuracy and the resolution of the simulation results that we get. This includes a couple of researchers oversimplifying the geometry of the cabin itself, like using jagged edges to approximate the shape of the luggage bins. Some researchers ended up using these boxes to really simplify airflow around a person. And clearly, airflow over a person is very different from airflow over a box. And there's also these simulations in which there's issues with the placement of the inlets and outlets for the air coming into the cabin. And what we find that if we want to get accurate results, we have to A, come up with accurate geometry, B, actually model those boundary conditions correctly to meet the correct configuration that we have in real life. And also thirdly, we want to be able to make sure that when we're considering the physical phenomena that occurs inside the aircraft cabin, we're thoroughly considering interactions in between different phenomena. So not only just looking at, for example, the turbulence effects, but also considering thermal effects and buoyancy effects as well. And so that was sort of the first step in my research, which is basically to be able to generate these higher resolution, accurate simulations that are actually about 3 to 5 times better than the existing research that's been done. And moving on from there, I then looked at ways to solve the problem of disease spread in aircraft cabins.
Okay, hang on a moment. Let me, at this point, I think I want to bring back Gilles into the conversation. Gilles, a lot of the things that Raymond is talking about, like higher resolution, higher fidelity of the model, and things like that, I've heard airline manufacturers talk about that. So, do you notice any difference in the way this 17-year-old genius is using your software and the way your typical Boeing, Airbus customers are using your software? What's the difference?
Well, that's a very good question. So you're talking about aerospace industry, and I know we talked about that, Kenneth, already. But if you think about it, many years ago, people simulation was mainly used by analyst group at those aerospace and automotive companies. But really, this changed dramatically. Now, simulation, virtual prototyping is used to design a really large range of products. You can think about products you use in your everyday life. Your cell phone will have a lot. Basically, your entire cell phone is designed thanks to simulation, but also some fans, your oven, etc. There is a lot of use in the biomedical industry, for example. Anything from hearing aids to decision tools for surgery. Again, the electronic industry to design chips and everything. So I wouldn't say that Raymond, from this perspective, used the tool differently than our customer, but I would say that he really pushed the envelope and enthusiastically used simulation to test his extremely creative ideas. What Raymond really did very well is he understood right away the value of simulation to test all the great ideas and concepts he had. He understood that by analyzing the simulation results, he could identify which idea was the best, as well as a way to make them even better. And really, what Raymond did differently, I would say, is that he was not afraid of using simulation technology, even if he didn't have a lot of experience with. So, while some may still see simulation as a tool for expert, Raymond really understood that it's a tool that every engineer can leverage, and he was definitely very successful at it. That his price definitely proves it. So, Raymond's use of simulation to design his new vent system is really the proof that simulation helps every engineers, designer, and innovators.
Okay, that's a very good point. I'm also going to bring back Raymond here, and I just noticed, for instance, Gilles, that in your title, you have a PhD, and I have always been under the impression that when it comes to digital simulation, most people who run digital simulations are people who are experts, people who have master's degree, pretty sophisticated, high-level experts. And here you have a pretty young man. So I want to understand, Raymond, where you picked up those skills for CFD that you're putting to good use now.
Sure, yeah. So, I've been involved with doing computer modeling for my various projects in the past, as well as through leading clubs like the robotics club at our school, in which I work with some underwater autonomous robots. And really making the jump from not only just using the computer to model, like using CAD modeling, but to actually do some analyses, such as with CFD. It was quite the learning curve for me. Basically, how it started was this was back in December, and I was listening to the news, and you just hear all these things about Ebola, as well as how they're being transmitted in aircraft. And what we kind of see from there is that it's really a huge issue. Let me bring into perspective some statistics here. In one example, a group of researchers actually found that a passenger with something like H1N1, when they walk onto a plane, they can actually spread that to more than 17 other passengers. And so we find that the really densely packed space of an aircraft cabin, it can really become an issue in terms of propagating these global disease epidemics. And so I started looking into existing research that perhaps people have been doing. And what we find is those issues earlier with non-representative CFD research. And so I essentially picked up the phone and I phoned Ansys and I made a cold call and said, hey, there's this huge issue with aircraft cabin airflow that people in industry are having trouble doing. I've been to a couple of national and international fairs with various projects in the past. I want to tackle this issue. Would you be able to support me? And I think they were. I'm very thankful for them to be able to support a high school student like me just out of the blue. And so moving forward from there, basically it was a combination of reading papers to understand what people are already doing in the industry and how we can improve on those results, as well as learning some solver theory, working, seeing how these partial differential equations work together, and taking a few online courses. And as well, after Ansys sponsored me the project, they were also kind enough to give me access to their database of training videos that they use to train people in industry. So really, not only understanding the theory behind CFD, but also understanding how I'm able to incorporate that theory into Ansys software and work with Ansys tools to really make these simulations happen. And what you see in terms of the end result is quite significant.
Okay, I think I want to see this end result now, and a lot of the people who are tuning in probably are eager to see it too. So if you have a way of sharing some of the animation, some of the things like airflows are obviously very difficult for us to talk about, but if we see it, it might make a lot more sense. So if you can set that up and maybe talk about the fix, the so-called fix that you came up with that you would like to recommend to the airlines to adopt, that would be wonderful. Now, while you're doing that, I also want to tell people who are tuning in that if they have questions for you particularly, or for Ansys representative Jules, they are welcome to plug those questions into the chat windows, and we have someone behind the scene who is kind enough to help us organize this and is monitoring the questions. So we would be sure to pick up those questions and try to address them as time permits and as we can. Raymond, turning the floor over to you now.
Yeah, thanks so much. So basically, before we go into the solution, first what we need to do is understand what's happening inside a traditional aircraft cabin. And so, as I mentioned earlier, I did some high-resolution simulations, and this really involves starting from scratch, creating my own CAD models that had those accurate geometry, as you can see here, preserving those contours of luggage bins, preserving those contours down to the details of, for example, the recessed windows that you can see in the model that I have here, and then also incorporating accurate modeling of the physics. And what we see in the traditional aircraft is this huge issue of disease spread. So in a moment, we're going to be watching a video of the middle seat passenger sneezing, and we'll be able to see that those bunch of pathogens not only spread cross-sectionally across the cabin, but also longitudinally inside the cabin. So let's take a look over here. We can see in the traditional cabin, person sneezes, and you've got these large swirling turbulent flows of air that essentially propagate the pathogens everywhere. You can see the adjacent passengers are at very high risk of getting sick. If we take a look at another view over here, you can see that longitudinal spreading of disease as well. And so it's clearly a very difficult issue. And now, with my multi-iterative engineering process, which we talked about earlier, is really the key advantage of using tools like CFD, I was actually able to test out various methods to change the way that this existing problematic airflow worked out in aircraft cabins. And so I was actually able to go through over 32 different scenarios, and ultimately I was actually able to come up with this patent pending design that I have over here. If I'm able to switch back to my webcam. Here we go. Yeah, so this is basically what I designed. It is a patent pending innovation that I call a global inlet director. And what we're able to do with this is actually install it in existing mount points already inside your traditional aircraft, for example, like your A320. And what we're able to do with this is just literally place a couple of screws on either side of this and install it overnight for the entire plane for about $1,000, which, if you think about it, is the typical price of a passenger's airline ticket. And the small change that we make with airflow in that regard has actually these great dramatic effects. If I move back to my screen over here, we'll be able to actually take a look at that. So here we have the improved cabin. And what we see here is the middle seat passengers he's going to sneeze again. And we're going to notice that huge difference in terms of these individual personalized breathing zones being created by the installation of my innovation. And what you're actually going to be able to see is that the pathogens are isolated just to that passenger. And they won't, because we're creating these virtual walls of air that come in between the passengers, we're actually able to prevent the cross-sectional and longitudinal spread of disease. So let's take a look over here. Middle passenger sneezes. And you can see that being eliminated right away without being spread to the adjacent passengers. So if we take a pause over here, you'll notice that these two passengers, they have their breathing zones completely clear of these pathogens because we're changing that airflow to now include, to now create these, essentially these curtains of air that prevent the spread of pathogens. And so taking a look at that from another perspective, we can also see that the way that airflow is now changed also prevents the longitudinal spreading of disease. And so what we ultimately also see is that numerically quantifying this using techniques like inserting numerical probes into my simulation flow field, what we find is a 55-time reduction in pathogen inhalation, as well as an improvement of fresh air inhalation of over 190% compared to that unmodified cabin that we saw before. And you know, one of the biggest things with CFD that some people get concerned about is whether those simulation results transfer into real life. And so to make sure that happened, I not only conducted, you know, standard error analyses, you know, making sure my results were, for example, mesh independent, that I was using, I was having good convergence of my solutions, etc. And by the way, I was actually able to, with Ansys software, as well as building my own computer, use meshes with cell counts of over 15 million and 20 million cells. And what we get from that is also an increase in resolution. But moving back to the idea of making sure that those CFD results transfer back into real life, what we can see here is that I've also constructed a scale model. And you know, by applying a couple of theories with the scaling of forces, we can actually see how that CFD results translates into real life. And if I were to play this over here, what we can actually see is that those same curtains of air being created and visualized by the fog that we see over here. And it really just shows that this innovation that I was able to create through my CFD analysis was able to ultimately apply to real life as well, and really become a feasible concept that could be economically and quickly implementable in real aircraft real soon.
Raymond, if you can hold up that little fix that you created again for the people to see, I have a question. I'm wondering how you managed to manufacture that. For instance, did you print it out in 3D printer, or did you have somebody mold it for you? How did you get it done?
Yeah, so basically what happened with my project is there was both a multi-iterative computational design phase, and as well the select solutions that came out of that got put through to physical testing. And so with physical testing, there were a variety of technologies that I involved, including, as you mentioned, additive manufacturing, so 3D printing, using both resin-based and gypsum-based technologies. There were also manual fabrication steps involved. And I mean, this particular prototype here was produced using laser cutting techniques. And what we find that's so interesting with this prototype is that this covers a typical window section. And you know, for a typical window section, this prototype itself costs $10 to make. And if we consider how many windows we have in the real plane, as well as we can really see how economically feasible this is. Not only at the prototype stage, but with economies of scale and mass production, we're able to further drive down those costs so that this really becomes something that is feasible and economically implementable for real planes.
Oh, wonderful. Stick around. I have some more questions for you, but I think it's good time for me to ask another question to Jules. So, Jules, if we can wake you up.
Yeah, I'm here.
And ask you something here. Now that you have seen the way Raymond used Ansys software, Do you have any suggestions? What else could Raymond probably look at now that he's already gone through the trouble of making a pretty high fidelity airplane cabin model and started looking at airflow? What else can he look at?
Well, I have to say, when I was Raymond's age, I didn't even know what simulation was. So maybe I'm the one that has to go to Raymond and ask for tips. But no, that being said, there's maybe two things he wants to explore actually. The first one is really don't not give up on simulation. There is never like a one single simulation that answers it all. Maybe he wants to test different cabin configuration for different type of aircraft. Maybe an A380 versus a smaller commuter jet, and make sure that the design is robust. Test it with full occupancy inside the cabin versus only 50% of the seat occupied, etc. That would be one aspect. The other aspect that I would think also very interesting is Raymond is probably already talking to people like Boeing, Airbus, and engineer at Embraer as well. And here's one thing he can do: all the simulation for all those different planes, right? He doesn't want to spend this time running them. He has better things to do. So maybe what he could do is actually take all this knowledge and really create an interface and customize and automate the entire simulation process so that other engineers can do the work for him. And maybe that will make sure that his product continue to be developed, but he will also have the time to focus on so many other ideas that I'm sure he has, and really so many other ideas that will help improve our lives.
So you're really talking about crowdsourcing large-scale simulation in through by publishing some kind of web interface or an app or a template, perhaps. Is it fairly easy to do in something like Ansys software, or would Raymond be going around looking for some other software tools to do that sort
No,
of thing?
it can actually do it directly with Ansys software. The solution is actually called ACT, or Ansys Customization Toolkit, and we see a lot of people really adopting that extremely. It's extremely successful offering, and that's basically what allows you to create those apps if you want, or automate a completely customized workflows and simulation process, so that even designer that may not know simulation, may not even have the time to learn it, can still benefit from it.
Okay, very good. Raymond, I think we are nearly at the end of our allotted time, and I'm just going to give you one last question, and it's the question that probably everyone is wondering. Did any airline manufacturers contact you and offer you a big chunk of money to buy your ideas, or what's next? What's going on?
Well, so yeah, I've been in talks. First of all, at the International Science and Engineering Fair, I've had the pleasure of having judges coming from the aerospace industry to speak with me about my project, and we've heard very positive results from companies like Lockheed Martin, Boeing, and as well there's a couple of organizations, including NASA and the Society for Experimental Test Pilots, that actually gave some awards to my project. And moving forward, actually in the recent summer months, I've been able to engage in talks with, including, for example, the Ventures Department of Boeing, as well as Air Canada, which is the major airline that we have here in Canada, as well as our local Vancouver Airport Authority. And we're just looking to see ways that we can get this from not only the prototyping stage that we have it at right now, but also to be able to move it forward through flight testing, regulatory approvals, and to really get it certified and implementable for a wide variety of aircraft. We brought up earlier the issues of, for example, could this work with aircrafts having different configurations? For example, different spacings of the seats. And would the airflow be the same if it was a full occupancy versus, for example, half occupancy? And so what we find is that actually with this innovation, what we're able to do is actually vary the angle of installation, and we can cover a variety of aircraft cabin sizes, and it makes it really easy to adjust for installation. And you know, as this also changes global airflow, what we see is that the airflow actually in terms of creating these curtains of air that come down in between the passengers, that does not vary based on passenger occupancy, which is really great, because now we have this economically feasible innovation that can be so widely implemented. And one of the biggest benefits of this is that it eliminates that barrier to entry, or barrier to implementation rather, that we've had with previous proposals in industry. So no longer do we have to pull like a 737 out of service for 1 to 2 months, perform something like a Type D maintenance check, spend tens of thousands of man hours, $5 to $7 million trying to redo the entire aircraft air conditioning system in the aircraft. What we can do now is, for the cost of $1,000, install this overnight right at the gate, losing the airliners zero money, and see those amazing results that we get with improvements in airflow the very next day. And I'll also, not only with the implementation stage, but I'll also be discussing my project at various conferences, including I will be giving a presentation at the Society for Experimental Test Pilots annual symposium coming up in September. And really the idea is to get the word out and get this innovation that I have here implemented as soon as possible. Because even as we speak, we have issues like MERS that are starting to break out. And if we don't do anything about the status quo, there are agencies that have estimated that the next damages could exceed trillions of dollars, in addition to millions of lives lost. And so by implementing these aircraft airflow solutions, I really hope to be able to make a tangible difference in terms of reducing the risk of pathogen spread and really improving the experience for these billions of people flying around the globe annually. And to really see that implemented real soon, so that we can make a difference as soon as possible.
Okay, wonderful. I think I can honestly say, and it'll be factually correct, that you are making me and many other people breathe easier when we go on the plane. So, Raymond, thank you very much for sharing your story with us. And I also want to thank Ansys for inviting me to moderate this webcast. I'm going to be blogging about it at Desktop Engineering Magazine, where I regularly contribute writing. So feel free to follow us, look us up, and I'm sure you can email Raymond or Jules or me if you choose to, although I think your questions are most likely to be answered by Raymond or Jules. This is all from here. This is the end of this Google Hangout session. Thank you very much. Kenneth Wong, signing off.